Let's look at the converse of the theorem we saw in the previous video. In this figure, we have two chords AB and CD. Let's join the endpoints to the center to get two angles. In the theorem we saw previously, we were given that the lengths of the chords were equal and we proved that the angles were congruent. In the converse, we are given that these two angles are equal and of course, we need to prove the chords congruent. From this given figure, let's jot down what we have been given and what we are asked to prove. This time, we are given that angle AOB is equal to angle COD. And we have to prove that chord AB is equal to chord CD. You would probably have guessed by now as to how we can prove this. Yes, if we prove these two triangles congruent, then we can surely say that AB is equal to CD. The congruence condition we are going to use is also very evident from the diagram. But let's write the proof systematically. We will focus on triangle AOB and triangle COD. These two sides are equal as they are the radii of the circle. We write OA is equal to OC. These two sides are also the radii of the circle, which gives us OB equal to OD. When you write this proof in your exam, you are also supposed to mention the reason next to each line. Like in this case, we got these two equations as each of these is the radii of the same circle. We can write equal radii next to these two equations. And we are also given that angle AOB is equal to angle COD. We can clearly see that it is a case of two sides and an included angle of each triangle. We get triangle AOB congruent to triangle COD by the SAS congruence condition. Side, angle, side. Therefore, AB is equal to CD as they are the corresponding sides of congruent triangles. Remember, if two chords in the same circle are equal, the angles they form at the center are also equal. And the converse says that if the angles formed by the two chords in the same circle are equal, then the chords are equal.